So now it's my pleasure to introduce to you our speaker for today, Monte Hamamoto. He's the CFO of Silicon Valley Clean Water. Turning it over to you now, Monte.
Well, thank you, Robert. I appreciate it. Appreciate the opportunity to talk to everyone today and give you a little overview of anaerobic digestion. Monte Hamamoto, I'm the Chief Operating Officer at Silicon Valley Clean Water, and been in the wastewater industry for quite a few years and been heavily involved in education of water and wastewater around the Bay, working with Solano College and Gavilan College down in Gilroy, and also through BAYWORK area Consortium for Water Wastewater Education, as well as BAYWORK. I've done a number. So I appreciate the opportunity. I look forward to going over a little bit what I can about anaerobic digestion in 1 hour. It's pretty quick, or 45 minutes. So we'll go ahead and get started. And please, if you have questions, please put them in the chat, and I'm happy to try to cover those at the end.
This is Corey. I just wanted to quickly say that we don't have a hard stop at the end. So if we go a little bit over, if people are willing to stay, you could do that. Or do we, Robert?
No, we shared that with Monte already.
See, I jumped in late. Sorry, guys.
That's okay, Corey. Thank you. All righty. Well, why do we even worry about digestion? And what do we do with our sludge that's produced at the wastewater treatment facility? Well, we need sludge digestion. We have sludge that comes out of our primary sedimentation process. We have solids that settle to the bottom, call that primary sludge. We have solids that float, and we call those floating solids, or scum or fog, which is fats, oils, and greases. And in the secondary treatment, we have trickling filter sloughing, and we have activated sludge and waste activated sludge that we need to pull out of the system in order to maintain the health of our activated sludge process. So we feed these sludges into what is known into a digestion phase, and there bacteria decompose the solids to simpler forms that are stabilized for final disposal. Real quick, I'm just going to touch on the differences between the two different types of digestion: anaerobic digestion and aerobic digestion. Anaerobic is the breakdown of waste by microorganisms in the absence of oxygen. They're encased in a sealed tank that is free of oxygen. And we have bacteria that use other chemical sources of oxygen that are within the solids and the waste stream that sustain their living and their metabolism. Aerobic digestion is in the presence of oxygen. And you can see aerobic digesters are uncovered. They're open to the atmosphere, so they can get oxygen from the atmosphere. But we're primarily focusing on anaerobic digestion because that is the most popular in the wastewater industry for numerous reasons, which we'll touch on a little later. Anaerobic digestion is where organic solids are decomposed by microorganisms, and they produce methane gas. And if you think about it, our stomachs are anaerobic digesters.
Hey, Monte, excuse me for a second.
Yes.
Just to do a technological check, your sound is going in and out periodically.
Oh, it is? Okay.
Yeah. I don't know if it seemed like it's relative to the online, the virtual world, but it doesn't seem like it's a problem on your end, but you can check it anyway. Just want to let you know.
Okay. Thank you. Appreciate that. I'll try to keep my head still.
Yeah, well, if it happens again or consistently, we could also have you take a moment just to call in, but let's see how it goes for.
Okay.
Why don't you do that, Monte? I think it's happened enough to know that there probably is going to be a continual problem.
So
Okay,
in order to do that, you click on the little lower left hand corner and go
what
to
I might be
audio.
able to do is just switch microphones.
That could help.
Sorry, everyone. Excuse us to try to get this right.
Yeah. Sorry about that.
microphone though. It might just be your connection.
It could be. Is my microphone better right now?
Can't really tell. It will take some time.
Let me see if I can switch my microphones here.
Okay, we just heard you go away. I think the phone call is probably the better way to go.
Sometime on Zoom, if you have a lot of people with the video on, the audio gets pretty choppy.
Interesting. Although most people have that off right now.
See if I can reconnect real quick. Technical difficulties. I was afraid of this. Sometimes a loose connection can be the problem. Is that better?
It's going to take some time for us to listen for a while, but are you still going through your computer or are you?
Yes, still going through my computer. Let's go ahead and try it. So far, so good?
Yep.
So far, so good.
Okay, it may have been a loose connection. I saw that it was a little loose, so hopefully that'll, I'll take care of the problem, but thank you. So getting back to anaerobic digestion, basically organic solids are decomposed by microorganisms producing methane gas. And as I was saying, our stomachs are anaerobic digesters. We have actually the same bacteria within our own stomachs that actually work. It's the same bacteria that we basically take care of in our anaerobic digesters. And as we all know, when we eat too much of certain foods, we can produce methane gas also. It's the same concept. So we're just doing it on a much larger scale. So there's two different bacteria in the anaerobic digestion process. One we refer to as saprophytic organisms, which are acid formers. They actually form volatile acids when they break down the organic solids. And then we have the methane formers, the gas formers, that convert the volatile acids as a food source for them to the methane gas. And we call them methane fermenters, and they're very sensitive to pH, and they reproduce in a pH range of 6.6 to 7.6. So when you talk to operators about anaerobic digestion, one of the things they watch very, very closely and they control is the pH of their digesters, and this is the reason they do that. The object of good anaerobic digestion is to maintain the suitable environment to sustain a growing population of both the acid formers and the methane forming bacteria. So properly operating digester, it's going to reduce the organics that you feed to it, the sludges, by about 40 to 60%. Think of the volume. If you have a gallon milk jug, you're going to basically come out of that with a little less than half a gallon. Most anaerobic digesters require a minimum of 15 days to reach this endpoint of reduction. And also at the end of those 15 days, they'll provide a reduction in pathogenic organisms, which are actually disease. They're indicating organisms that disease-causing organisms can be present. So we want to make sure that we reduce the pathogens, so the solids that we do produce for reuse later on are safe to use and not going to have any harmful diseases associated with them. One of the regulations that we follow that regulates the formation of biosolids and the disposal of biosolids, it's the 40 Code of Federal Regulations, Part 503, and they have a process to significantly reduce pathogens called the PSRP. And it states that biosolids are treated in the absence of air, which is anaerobic, for a specific mean cell residence time, which that means how much time that it spends in that environment at a specific temperature. So what they want is they want 15 days residence time, and they want the temperature to be between 35°C and 55°C, and 60 days at 20°C. So you can have it at a little less temperature, but you have to keep it in there for a longer period. But at the end of 15 days, between 35 and 55C, which our target in our digesters that we run at SVCW is around 95 degrees, same as your body temperature. So we try to mimic. That does the best for reducing the solids, the organic solids, and also to provide our reduction in pathogens. There's another thing that operators watch very closely, and that's the buffering capacity in a digester. And the buffering capacity is a digester's ability to resist change in pH. So if you think about acids and bases, remember when we're adding food or organics to the digester, the bacteria are breaking it down to volatile acids. Well, those are acids. So acids are going to reduce the pH. The methane formers, they are very sensitive. That pH has to be between 6.6 and 7.6. So we want to make sure that there's enough what we call alkalinity to neutralize or buffer the acid formation. So it keeps that pH in that neutral 6.6 to 7.6 to make sure that our methane formers are nice and healthy. In a well-operating digester, the volatile acids are usually expressed as acetic acid, and they would be in the range of 50 to 500 milligrams per liter, or 500 parts per million. And the alkalinity expressed as calcium carbonate would be in the range of 2,000 to 3,000. Ours run, the volatile acids are around 100, and we run about between 2,000 and 2,500 on the calcium carbonate alkalinity. And what the operators watch is the volatile acid to alkalinity ratio. And so if you do a division, take your volatile acid concentration and divide it by your alkalinity, you should have a ratio, and you want to keep that ratio as close to 0.25 or less. And that means you have plenty of alkalinity to handle any big shots of volatile acids that you might have. It have plenty of buffering capacity, so it won't affect your digester. It's just like our stomachs. What do we do when our stomach gets upset? We take a Alka-Seltzer or a Tums or some kind of calcium carbonate. And what it does is we have too much acid on our stomach. That's going to make the stomach upset. You're not going to feel good. You're going to produce a lot of gas. And by putting in that Tums or that calcium carbonate, you're going to neutralize that acid, and you're going to get that pH back to where the bacteria are happy. So how it works is the complex organics is what you're feeding into the digesters. You have your acid-producing bacteria, which are breaking down those organics into organic acids and hydrogen. Then from there, the methane-producing bacteria are taking those organic acids and converting it to CH4, which is methane, and CO2, which is carbon dioxide. For those of us that like to geek out a little bit, this is a little more in-depth and detailed on kind of a scientific note. And it just goes through a little more detail of how that happens. For those that are interested, you get your organic food particles. It breaks it down into proteins and carbohydrates and lipids, amino acids, sugars, and fatty acids. Then your fermenters actually break it down into acetate and your volatile acids, basically. So it's taking these complex proteins through a fermentation process, breaking it down into your fatty acids and volatile acids. Then from there, it's taking those acids, and this next step is when it breaks it into your gas formers, which are taking and basically producing methane and CO2. And on the other hand, it's producing hydrogen, which then turns into water and methane. So just a little more detailed of how that happens. The other slide was a lot simpler. But I see we have quite a broad spectrum of people in the class, ranging from engineers to chemists to plant managers to people that just want information that aren't even in the industry that want to learn about anaerobic digestion. So hope I didn't go a little too far in depth. But one of the things that's very important, every treatment plant has what we call design parameters. It's how the engineers designed the plant to work. So we talk about volatile solids loading on your digester. That's basically the food that you're going to feed it. And it talks about the ranges of how many pounds of volatile solids you could feed per cubic feet of digester space that you have, or volume. The detention time, 15 to 25 days. How much volatile solid reduction you should have after those 15 days should be 40 to 60%. Gasification of your solids. This is breaking down the solids and the methane gas formation. And then digester gas production, how much digester gas will be produced, that's methane basically, and CO2, for every pound of volatile solids is destructed. So all of these are actually from SVCW, right out of our O&M manuals. And so we have these design parameters, and we always refer back to them, which when we do a math problem at the end, I'll show you how all of this works and how you can really tell if your system's working properly. So mixing is one of the most important factors in the high rate digestion process. That way you can, as you fully mix it, think of a mixer, you're mixing up pudding. You want to make sure you mix all the pudding. You don't want some of the dried pudding left on the side of the bowls. So you want to be able to get good mixing to where you use almost all of the digester volume. There's no dead spots in there. Everything's getting mixed. Also, as you're putting food in there, you're quickly distributing the food throughout the volume, and you're putting the microorganisms in contact with the food. Rather than them swimming around trying to find the food, you're actually bringing the food to them, which is actually helping things progress. It kind of speeds up the activities. Also, you're achieving good pH control by distributing that important buffering alkalinity. You want to make sure that's all the way through the digester. If you don't have good mixing, you can have alkalinity in the digester, but if you're only feeding your organics in one side and it's not mixing, you'll have a pocket of acid that won't be neutralized by the alkalinity. So you want to make sure everything is mixed up really, really well to make sure you have continuous pH control throughout the entire digester. Also, it distributes heat throughout the tank, and it's important, and we'll talk a little bit more about the heat. And it minimizes the separation of heavy grit and floatables. What also happens in a digester, you're going to have a little bit of grease mixed in with your solids. What'll happen is you just have poor mixing, the grease will float to the top and you'll create this giant grease mat in your digester. And then your grit and heavy things that are in there, sand, eggshells, coffee grounds, those kind of things, those will settle to the bottom if you don't have good mixing. So you'll just have like the middle section of your digester volume working, and you'll have the upper section not working because it's full of grease, and you'll have the bottom section that's building up with grit and solids that's not active. So by keeping everything fully mixed, you'll get the most out of your digester volumes. So we'll talk a little bit about digester operating temperatures. In the industry, there's 3 ranges of temperatures. There's psychrophilic, which is the lowest temperature. It's an unheated digester. You're basically dependent on ambient temperatures and very little bacterial activity at temperatures below 50 degrees F. So I don't see many of these. Actually, to be honest with you, I've never seen one of these in use at a treatment plant that I visited. There's the mesophilic range, which is the mid-range. Medium temperatures, most popular, this is one we usually see, and it keeps the temperatures between 80 and 113. And most of the time, the set point's around 95. There's also a thermophilic, or a hot temperature, and those are above 113. And those are starting to become more popular. they're just energy. It takes a lot of energy to keep that digester that hot all the time and fully mixed, but it breaks down the solids faster. So if you're having an issue with digester capacity, you have more solids coming in than you can really handle. You might think about stepping up to a thermophilic situation if your system will support it, and you can actually process those solids in less than 15 days, which adds a little more capacity to your system. There's also something you don't see them very often anymore in the industry, but some of the older plants will have secondary digesters. But there's no mixing. Basically, they're storage. You have the nice stabilized solids that go into a secondary digester. It allows the solids and the liquid to separate. The solids will go to the bottom, the liquid will stay on top. You can draw the solids off, and you'll be able to draw the solids out they'll actually be heavier and thicker when you go to a dewatering phase, which is after digestion. Also, some people use these as gas storage. So you'll see some plants, I know the city of Richmond has what we call die stores, and they have these, they're expandable lids. They're basically like a big balloon. And you'll go to the plant one day and the balloon's all big and full, and then the next day, it'll be collapsed like a bad souffle. But that just means that they weren't producing enough digester gas to store. They were using more than they were producing. But it's a way to be able to store digester gas. But again, this takes up real estate, and a lot of places choose just to put in gas storage system where they can actually take the gas, pump it into a tank, compress it at a higher pressure so they can get more in there, which uses less property instead of using a big giant space for a secondary digester. Let's talk a little bit about the digester gas system itself. Digester gas, it's pretty valuable stuff. It has a heat value of 500 to 600 BTU. Where natural gas has a heat value of 900 to 1200. It's not quite as efficient as natural gas because there are some impurities in digester gas and the methane concentration isn't quite as high, but it does have value. Biogas will burn at 55 degrees or 55% methane, and biogas with at least 62% methane can be used as a fuel source. So digester gas is we use it for cogeneration. We have big engines, Enbacher engines that turn GE generators, and we can produce 1.2 megawatts of power that we use to sustain our treatment plant. And now we have just got the ability to export power. If we produce too much, we can actually put it back out on the PG&E grid. We also just installed 1 megawatt of battery storage. So we can use this power that we're generating from burning the digester gas or the biogas, and we can use that energy to recharge the batteries. And what that does for us is when we have a very big peak demand of power, especially during the summer months when we have peak power costs, we can actually take those batteries that have all that power storage, and they can actually discharge, reducing our demand on PG&E power. If our cogen units aren't making enough power, the batteries will supplement it and get it up there to where now we're actually saving money on demand charges. And we're looking at saving a considerable amount where I'm not sure exactly how much these batteries cost, but we said we can pay back, have a return on investment of about 6 years on those batteries. So we're always looking on ways to make things more efficient. We also use it when we need to use our boilers to heat the digesters in the buildings. Some places use internal combustion engines to operate blowers for aeration. Some places use the extra heat for biosolids drying. I know the city of San Mateo has a natural gas system when they can actually fill up vehicles, trucks and city vehicles. And then I put this down, there's a production of biodegradable plastics, and that's something that we've entered into research and development with a company called Mango Materials, where they're actually taking methane, feeding it to a certain type of bacteria that they've been able to develop. And one of the things the microbes produce as one of their byproducts is this biodegradable polymer, which can be turned into plastics, which are fully, truly biodegradable plastics. It can actually fully degrade within 1 year in a landfill. So if you throw that plastic bottle that's made out of this particular biodegradable resin, it will fully degrade within 1 year. Also, the cool thing about it is you can take those plastic bottles, in theory, grind them up, bring them back to the treatment plant, and feed them back to the digesters as food source. So it's a total recycling. So we're very excited about working with them, and they've just put in one of their scaled up systems at our plant, and it's looking very promising. You can see we have cogeneration engines, there's boilers that'll heat the digesters, there's natural gas vehicles, which you can see these buses and garbage trucks. So biogas is a very, very big commodity in our industry right now. I want to talk a little bit more too about safety. Safety is always a big deal in the wastewater industry. Just when I first got into the industry 30 years ago, the wastewater industry was on the top 10 most dangerous jobs. There was a lot of deaths and injuries in the wastewater industry. A lot of those were in confined spaces. A lot of it had to do with lockout, tagout, engulfment. I mean, there's a lot of things, chemical exposures. So there's a lot of things, hazards that we work around. One of these things is you have a giant tank that has a bunch of gas in it that's actually a combustible gas that can explode. What you must do is keep these digesters, and from the picture you saw in the beginning, they have like a dome on the top. You always wonder, why aren't they flat? Why are they domed? Well, you want to keep them domed so you have a space in there to store gas. And you want to keep a positive pressure in there, and we usually keep less than 11 inches of water column pressure in there. If you get higher than 11 inches, you could result in gas escaping from the dome from either your seals, or if you have something plugged up, it could actually, cause the pressure to actually break the top of your digesters, and I've seen them crack. The other thing is you must keep them out of a vacuum situation. You can't, if you draw your solids out, remember this is a closed tank. So if you pull the contents out too fast, you can create a vacuum, and that lid that had a dome on it, guess what? Now it's like a bad souffle. You just caved in your dome. You actually sucked it in. So you want to make sure when you're withdrawing solids from your digester, you're not doing it too quickly. And you could also, if your safety devices aren't working properly, you could pull oxygen into that atmosphere. Now you have methane, you have oxygen. All you need is an ignition source, and you have a bomb. So you want to make sure you don't get oxygen in your digester at any way, shape, or form. There are safety devices, or pressure vacuum relief valves. The pressure relief generally has a flame arrestor attached to them, so if anything does catch on fire, it can't make its way back into the digester. And you can see digester gas, get some oxygen in there, and this is what can happen. And I believe this happened in the Midwest. So it's very serious. It's something we watch as operators very closely, because we know these things can happen, and we want to make sure we don't have it happen at our facility. So here's those safety devices, and you'll see these sitting on top of the digesters. You'll see that square box in the bottom, what they call pressure vacuum relief valves, is a flame arrestor, and it's a series of aluminum plates where the flame actually has to make its way through these plates, and generally it can't. So it actually blocks any flame that may be from the outside, and it blocks that flame from getting back inside the digester where the gas is. These will have a pressure relief valve on them, plus they'll also have a vacuum release. So you won't, You won't have that problem of overpressurizing, and you won't have that problem of creating a vacuum. So these are very important devices. They need to be on your preventive maintenance list. They are on ours. We check these monthly, and we want to make sure they're working properly because they can actually lead to a big problem, and we don't want to end up with this if that fails. Also, excess gas produced can't be utilized. It can't be utilized. It's prohibited from discharge to the atmosphere by, in our area, it's the Bay Area Air Quality Management Board. And remember, methane is a greenhouse gas. So you don't want to just release that into the atmosphere. If you're producing more gas than you can use, you need to burn it. And by burning it, there's different ways you can do. Now the Air Board is really focusing on this right here, which are fully enclosed waste gas burners. You'll never see a flame on the outside. The flame is internal and has a catalytic converter in it. This is the old type. We call these the old candle waste gas burners, and you can actually see the flame from the top of them. And this is just excess gas that you're not using. If you burn it, it makes it safer to be released into the atmosphere. But we actually have a limit on how much we can burn and release into the atmosphere. So the Air Board says we can only burn so many tons of gas per year, and we have to monitor that and watch that very closely. Heating is also important. Remember, it's just like your stomach. You want to try to keep your body temperature around 96.8 degrees. Our digesters, we're going to try to keep them around 95 degrees. There's different ways to do this. You can actually have a boiler which creates hot water. The hot water goes through what we call a heat exchanger right here. And this is a spiral heat exchanger, very popular in the industry. The sludge from the digester will be pumped in through the dark ring, and then hot water will go through the white ring. And they're actually a very thin sheet of metal that separates the two. And the hot water will transfer heat into the sludge as it's put back into the digesters. So this is one way that we can heat the digesters. And you can see this is a spiral heat exchanger with the rings we just showed you, and this is what it looks like on the inside. And then there's also another type where you have a big giant, like a hot water heater, that's like a big hot water bath, and then you run these sludge tubes through the hot water bath. This is a firebox that heats the hot water, and the hot waters are circulated around these tubes. Sludge is pumped in, goes through these tubes. They're very thin, and it'll transfer the heat. So that's how we can maintain that 95 degrees. So the different types of mixing systems, remember, mixing is very important in the digesters. There's different types. There's mechanical mixing, which you can use like a big propeller, like, you know, a regular stand mixer. You're mixing cake batter or pudding. And there's pump mixing. We're actually pumping it out of the digester through like a heat exchanger or some other form of process, and then back into the digester. You're pumping it out and putting it back in. And then there's also a gas mixing type where you're actually taking some of the digester gas, you're putting it into the digester, and you're allowing the release of those gas bubbles, and the gas bubbles will be effervescent, and that'll actually cause a mixing action. Generally, the gas mixers are located in the bottom. The gas wants to rise, and as it rises, it will pull the sludge with it, and it will create turbulence in the digester, which will provide your mixing. So just some examples of mechanical mixing. There's some places that have these big giant mixers that come in through the side like a big blade. There's some where you can actually pump mix, where you pull it out and then you pump it back in, and it goes through these nozzles in different directions. So you're actually pumping it. You can see it pumps it in different directions to keep it totally mixed. And then your gas mixing is you have your lances at the bottom releasing the gas, and they'll actually go and actually do like a circular motion. And that's how you can mix your digester contents with either gas mixing or mechanical mixing. There's three main operating controls of a digester. If you talk to any operator, they go, well, digesters are kind of this black box because you can't actually go in and see what's inside of it because it's all sealed, and you just kind of guess what's happening in there based on the lab results that you get out and how much gas you're producing. But the three different things that the operators have control of to make sure that digester is operating properly is keeping the temperature at 95 degrees, heating it, you're feeding it, so how much food you're putting into it, and then mixing. You maintain good contact with the food and the microorganisms. So the operators, they're checking the mixers every shift. They're constantly watching the feeding. It's actually all monitored through our SCADA system, which has flow meters on it. It says you're putting in this many gallons of solids or this many pounds of solids. And we can actually adjust that by adjusting the pump speeds, and actually timers. Some places use timers. They'll let the pumps kick on for 15 minutes and then they'll be off for 5 minutes. So there's different ways to control that feeding. The temperature, again, you want to maintain the optimum temperature, and you want to make sure that temperature is maintained so you can properly reduce those volatile organic solids, and you want to make sure the temperature is right for those delicate methane formers. Feeding, you want to maintain the proper balance of volatile acids and methane fermentation. Basically, you don't want to feed so much volatile acids that it produces so much acid that it actually uses all that alkalinity buffer that you have. And, you know, we've all had what we call a sour stomach. Well, we use the same terminology in the wastewater business. We don't want a sour digester. I've been there, I've done that. And that is one of those days where you're lifting 50-pound bags of sodium bicarbonate up on top of the digesters, and you're dumping in a big giant Alka-Seltzer. And it takes a lot to get this alkalinity back up and to get these methane formers back in good shape where you're producing gas. And also you want to maintain the optimal, we call it percent solids. That solids, we want to keep that solids as thick as we can and still be able to pump it into the digesters. Because what happens is, think about, we're pumping something that has a consistency of a really nice thick milkshake, about 3.5% solids. If we add a lot more milk to that milkshake, it becomes a lot more liquid. So we're actually pumping in more water into the digester. What that does is now we have to heat that water. That water's cold. So that puts a demand on our heat. Also, that water's in there and is taking up that valuable volume of your digester. So you want to make sure that you keep the solids as thick as you can in order to not reduce your volume of working capacity. And also you don't want to cool your digester down. And mixing. Again, we talked a lot about the mixing part. You want to provide that good heat distribution. You want to provide that optimum contact between the food and the microorganisms. You want to make sure that all of your solids are in suspension, the stuff that can float, the stuff that can sink, and then the organics that are in the middle. So you want to make sure that your mixers are in good condition and mixing properly. So getting to a little bit of math. During a 24-hour period, 2,800 gallons of 6.5% total sludge solids with a volatile content of 68% was pumped to an anaerobic digester. So basically what we're saying is we put 2,800 gallons of pretty thick solids into a digester, and that solid content had 68% of that is stuff that can be converted into volatile organics or volatile acids. The rest of it could be inert stuff. It could be grit. It could be other things that aren't going to be digested. It's just going to come out, go in and come out. Nothing's going to happen to it. But 68% of that 2,800 gallons that you're putting in there, we can reduce. So the first question is, how many pounds of dry solids were fed to the digester? And the second question is, what portion of the solids are volatile organic that can be readily digested? So we have in the industry what we call a pounds formula. And it's basically your flow, which we have all of our known information up here, and what the percent solids are in decimal form, and you multiply that times a constant, which is 8.34 pounds per gallon, which is the weight of water. 1 gallon of water weighs right around 8.34 pounds. So when you plug in the numbers that are up top and you do the calculation, you come out with 1,518 pounds of dry solids. Okay, that's how many solids were in that 2,800 gallons. If you took all the water out of what was pumped in there, you have 1,518 pounds of solids left. Okay, so why is that important? Well, now we want to find out how much of that was actually volatile that will be broken down in the digester to produce the volatile acids that we need to produce gas. So we know 68% of the solids that were put in there, the 1,518 pounds, 68% of those are volatile solids. So we have a total of 1,032 pounds of volatile solids were pumped into that digester during that day. Okay, so remember this number. Now, we know we have the same math problem here somewhat, but we're going to want a different, some different information from that. We pumped in the same 2,800 gallons, pumped in a 24-hour period. And we have an anaerobic digester with a diameter of 40 feet and it's 20 foot in water depth. So your volume of that digester is 40 by 20. The raw sludge had a 6.5% solid, the same as the last math problem. And it's the same, the volatile solid content of the 68% contained 1,032 pounds of volatile acids. So we already did this math part. We have this many gallons. We know our raw sludge was this percent solid. Calculated that, and we know 68% of that is volatile. So we know we have 1,032 pounds of volatile solids. So we want to calculate the digester loading in volatile matter per cubic foot per day. And we'll find out why this is important to know. So we know this is all the known things that were given to us in the word problem. So we go, okay, well, we know one of the things we have to find out is what is the digester volume? And the digester loading calculation is the volatile matter added divided in pounds per day divided by the volume of the digester in cubic feet. So taking all of this information that we have, first we'll break it down and we'll go, okay, what is the volume of the digester? We have the diameter of the digester and you multiply that times 0.785, which is a constant. And that's a breakdown of pi. If you're dealing anything with circular dimensions, you're always going to have some form of pi in there. And then you multiply that times the depth in feet. So we know we have 40-foot diameter squared times 0.785, our constant, and is 20 foot in depth. You do the calculation, and we know we have 25,120 cubic feet of space inside that digester. So we have this bottom part of our equation. We know from the previous calculations that we have 1,032 pounds of volatile solids or volatile matter that we fed into the digester. And here's our cubic feet of digester volume. You do the calculation and you come out with 0.041 volatile matter per cubic foot per day. Why is that important? When you go back to that previous slide on our design criteria, it'll say you need to feed this digester at this rate and it will work fine. So where are we? And excuse me, there is a typo. This is supposed to be 0.41, not 0.41. But when you look at that, we are right in the range of our digester working correctly. So if an operator calculates this out, which they do on a daily basis, and they come out with the correct answer of 0.41 volatile matter per cubic foot per day. In our high rate digester, we are within the working range where we should be. So we know our digester feeding is correct. This is another popular question that you'll see on certification exams. It'll say, okay, you have an anaerobic digester, it has a feed volatile solid content of 68%, and a digested sludge overflow. That means after it's all been broken down, how much of that solid is left is volatile solids in what's been fully treated. And so that's 43%. So you have 68% solids going in, you got 43% volatile solids coming out. So it's like, okay, how much did we actually reduce the volatile solids going in? So the volatile solids calculation is in minus out divided by in minus in times out, and turn that into a percentage. When you plug these numbers in, you'll actually come out with 64% volatile solids reduction. And when you look at back at our design criteria, I believe we are between 40 and 60%. So we're actually working out a little bit above what our design criteria is, which is actually a good thing. We can actually push our digesters a little more than the engineers thought we could. So this is just a way to check your digester against the design criteria, and are we operating it properly? And this is a good way to check that. Like, okay, well, why are these, what's this information important? Well, we did previous math problems and we came up with, we're feeding the 1,032 pounds of volatile solids to the digester. We achieved 64% volatile solids reduction, which is pretty good. How many pounds of the volatile solids reduced? And we go, okay, well, we knew we had started out with this many pounds, 64% of those were reduced. So we actually reduced 660 pounds of volatile solids. It's like, okay, well, why is that number important? Well, if you look at gas production, we produce 14 to 18 cubic feet of biogas per pound of volatile solids reduced. Okay, so how many cubic feet of biogas did we produce when we reduced the volatile solid content by 660 pounds? So the 660 pounds of volatile solids reduced, and I just took a number kind of in between these at 15 cubic feet of biogas per day or per pound reduced, and we produced 9,900 cubic foot of biogas. Okay, great. So we produced some biogas. What does that mean? It requires approximately 19 to 21 foot of biogas to produce 1 kilowatt hour of electric power in an internal combustion engine or cogen engine. So if we produce 9,900 cubic feet of biogas, and I took the middle number here again, and we need 20 cubic foot of biogas to produce 1 kilowatt of power. With that same amount of biogas, we can produce 495 kilowatt hours of electric power. And that's a fair amount of power. I mean, we use, right now, we're using around 1.4 or 1,400 kilowatt hours, or 1.4 mega, nah, yeah, 1.4. So we're producing, with this amount of biogas, we're producing about a third of the gas that we're going to need. Right now, that's just this with this calculation. But if you calculate what we actually do today and some numbers that I actually saw this morning in a meeting, we're actually almost energy neutral, especially at night. We're producing 100% of our power, which is exactly what we were hoping to do. So if there's any questions, I'm happy to answer them. I've enjoyed talking to you all. I hope you learned a little bit of something. And I'm always available. Again, I think you'll get these slides. I believe I put my contact information on the front slide. So if you do have any questions, you can always email them to me. Always happy to look, answer any questions I can. And I have quite the network of wastewater individuals that are way smarter than I am. And I can find the answer for you if I don't have it. And I'm happy to help.
Great job, Monte. We're getting a lot of comments of thank you and from about your presentation, but also there's a question here. For Dean, he asked, can you talk about digester cleaning a little bit?
Digester cleaning. The people that clean digesters are very special people. The ones that I've run across in my lifetime and the ones that we've had the digesters cleaned in SVCW. It's a company, gosh, I think they come out of Nevada, but they've been doing it for a long time and you have to have very experienced people to do it. The hardest part is taking the digester down. It's actually remember, you don't want to add oxygen to that digester, but you still need to get the water out of it so you can open up your hatches that can access the inside of your digester for those guys to actually climb down in there and vacuum and suck all the solids that have settled in the bottom of your digester and all the other fun stuff that they find in there. We use a purging system. We actually get big containers of nitrogen. And as we're drawing the digester down so we don't create that vacuum that'll pull our lid in, we keep the pressure up with nitrogen. We'll pump nitrogen in to keep that airspace free of oxygen as we're pumping down. And eventually, once we're pumped down to a level to where we can open up the manways, now you shut everything off. Actually, before then, let me back up a little bit. One of the things you want to do is you want to shut your digester down so you don't produce any gas. So basically, you want to kind of kill your digester. And that way you're not producing gas. And then as you draw it down, you can pump nitrogen in there to create that pressure that you constantly need so you don't suck the dome in. Pump your solids down. Then when you get it down to a level where you can open up your manways, you're just releasing nitrogen in the atmosphere, which is, according to the Air Board, it's not a bad thing. And that's how we do it safely. The companies come in, they have a lot of pumps, a lot of big hoses, and they pump that contents out generally to some kind of a screening rack where they can screen all the rags and other things that get in there. And then we can either put it back into the process or we can pump it out to our drying beds. And we choose to pump it to the drying beds. And we'll go ahead and dry those solids, and then we'll go ahead and remove those solids and use them for land application. One of our land application sites in Solano or Merced or Sacramento County. But yeah, if you need any information, I believe we have the number for the digester cleaning company that we use. And we were looking for an SOP that we wrote a long time ago for that, and we have not been able to find it. But if we find it, I can sure share it with you, Brian.
Wonderful. I have a question from Robert Thompson. Is there any initiative to allow excess biogas to be used for additional purposes instead of burning it?
Yes, absolutely. And we're trying to find those other areas. One of the things we're looking into, we have a couple of people or a small team working with a company called Bloom Energy, which is fuel cells. And basically they'll take that gas and they'll use through a chemical process, they're able to generate electricity in the fuel cells using digester gas. And one of the things, cogen engines are about 26% efficient. The gas you put in, you get about, out of that gas, you get about 26% efficiency with the electricity that you produce. With fuel cells, it's as high as 56%. So for that 1 cubic foot of gas, you're getting 56% energy instead of 26% energy. Much more energy efficient, and we're looking at possibly running both. We're looking for another way to utilize that biogas so we hopefully don't have to flare off any, and we can totally use it, turn it into some kind of renewable energy, and capture it all. The other thing we're looking into is CNG for vehicles. There is some interest possibly with local garbage companies to do that. The only problem that we're having is the electric cars and electric trucks. The advance in that technology is so rapid that CNG may be a thing of the past for powering cars and things. So we're looking for alternatives. And again, we're looking at mango materials as a potential avenue to reuse and recycle our biogas. The other thing we can do is we can put it back into the PG&E gas system too. We can run it through highly purified purifying systems, take all the impurities out and put in natural gas quality back in the PG&E grid. So we are looking for ways to do that because we don't want to burn our gas either and waste it in waste gas burners.
Wonderful, Monte. One more question. You mentioned increasingly popular thermophilic systems. How does that for pathogens at higher temperatures?
The higher temperatures actually is good. It actually will help break down the pathogens also. Pathogens are pretty delicate organisms, and a higher temperature and a high rate, we call them high rate digesters. A lot of your egg-shaped digesters are high rate digesters, and some of them are operated at thermophilic conditions, and you do get good pathogen destruction at the thermophilic range also.
Great. We got a lot of great comments saying that you did a great job, Monte, that the information was very helpful and it was a good presentation. And we thank you, Monte, for being with us today. So we hope that you have a great rest of your day, and thanks for joining us today. And Monte, wonderful as usual.
Thank you, Robert. Thanks, Corey. Thank you, everyone.
Thank
Be
you.
safe out there.